Analytical Chemistry 1, Lesson 21. Reactions are always working to reach their equilibrium point. The Gibbs energy is continually being spent until it reaches its minimum. This is the equilibrium point of the reaction. If the reaction concentrations are such that a calculation of delta G is negative, then the reaction proceeds forward as written in the equation. And if it is positive, the reverse reaction occurs. The concentration of the participants will continue to evolve until equilibrium is reached. At this point, both the forward and the reverse reactions are still occurring, but they are occurring at equal rates, so that the concentrations no longer change. But the chemical dance of reactivity is still occurring at the pace set before, but now it is balanced in this very dynamic equilibrium situation. Take a look at our Gibbs reaction equation. Equilibrium is achieved when delta G equals 0. Q takes on many values during a chemical reaction, but it is always evolving towards one specific value, the value it assumes when equilibrium is reached. This is a specific value of Q that is only acquired at equilibrium. Indeed, equilibrium is defined by this value of Q for this particular reaction. Because it is a special value, we rename it K, the equilibrium constant. And by arranging the equation, we obtain the relationship we know from first-year chemistry. Delta G naught equals minus RT ln K. Delta G naught is a constant unique to a particular chemical reaction at a specific temperature. Unlike delta G, which is continually changing throughout the reaction, delta G naught is a defining constant for a reaction. Likewise, K is a constant for a reaction, specific for a given temperature. Q is continually changing throughout the reaction until Q reaches the value of K. Delta G naught is a value that depends upon our choice of standard states. Therefore, K is also dependent upon that choice. When we pull such values from tables, we need to make sure that the reference standard states are the same as the ones that we intend to use, like molarity versus molality or atmospheres versus bar. But tables that report delta G naught for a reaction could just as easily report K for that reaction. They are the same thing. However, tables generally record formation data from which we could calculate delta G naught for a particular reaction. K, however, is specific to a particular reaction. So delta G naught information is generally recorded for specific and atomic and molecular species, while K is recorded for specific reactions. Some things to remember about delta G naught and K. You have a reaction with its particular delta G naught and K. The reverse reaction just changes the sign of delta G naught, but it takes the reciprocal of K, 1 over K, for its equilibrium constant. Equilibrium constants are always positive, but they can be less than or greater than 1. If you are applying Hess's law to a few equations and summing them together, you similarly sum delta G naughts. It's a state function. However, you multiply the various K values together to find an equilibrium constant for the summed reaction. Now, both of these concepts arise because of the logarithmic relationship between changes in Gibbs energy and the equilibrium constant K. These next two observations are helpful in making quick assessments. Can you see how to reason it through if you forget which is which? K has products in the numerator and reactants in the denominator. A large number means that the concentration of the products is greater than the reactants. Conversely, a small number suggests that the reactant concentrations is larger than the products. Remember the difference between delta G naught and delta G. Delta G naught is a constant for a reaction at a specific temperature. It is the goal to which the reaction aspires. The sign of delta G indicates the direction the reaction will proceed to reach equilibrium. At equilibrium, delta G naught still has the same value as ever, but delta G has gone to 0. Finally, there are some named reactions, equilibrium constants worth mentioning. They pop up in scientific discussion all the time. So acid dissociation and base hydrolysis are the key reactions in acid-base reactions. The solubility product is associated with the reaction which sees the dissolution of a solid into a solvent. That's useful when a solid is only weakly soluble. And the formation of complex ions is described with the equilibrium constants for those processes.